Yale working with Marla Jihawk, and then she moved a couple years ago to Harvard Center for Astrophysics, where she's a theory and computation fellow. She works on stellar streams and the Milky Way, and she's going to tell us some of that stuff today.
Yeah, so it's been a really exciting time for the Milky Way Science, and I'll be mostly talking about this one stream with the new Gaia data, and tell you what you can tell us about the nature of dark matter. And so the reason we're asking this question is because cold dark matter model seems to be very good on large scales, and so I'll just, yeah.
Oh, you're taking a chance about careful, yeah.
Like turn off.
Well, most likely in front of everybody.
Yeah.
Stay away from it.
So here's, I'll show a movie that shows the distribution of galaxies as observed in SDSS, and then the distribution of dark matter halos on the other side, as seen in a Bolshoi simulation. And so if you kind of look very carefully, you can see like that there is a dividing line, but kind of looking as a whole, the distribution of galaxies on large scale is very similar to the distribution of dark matter halos that are simulated. And so this is a really remarkable success of this lambda CDM model predicting the distribution of matter on large scales. And so this is why we thought it was a good model to kind of follow up on and see whether it holds on the small scales as well. And then something like 20 years ago, people noticed that if you zoom in on just one tiny dot in this picture on an individual galaxy size of the Milky Way, in the dark matter simulations, you're expect to see something like on the left-hand side. So there should be just a lot of structure and smaller clumps of dark matter in this one larger halo. Whereas when we look into the Milky Way, so here I'm showing the distribution of dwarf galaxies from the recent review by James Bullock and Mike Bell and Colchin. We see that there are satellites of the Milky Way, so smaller galaxies orbiting our own, but not nearly in the numbers as expected in the simulation. And so this was called the missing satellites problem, and it was some tension between the CDM model that looks like it doesn't really work on small scales. And of course, people then studied this in like try to find the middle ground coming from both sides. So the satellites here you see in red are galaxies discovered since 2008, and you've probably heard here as members of the ES a lot of those are, especially this contingent over here comes from that survey. So there's been more discoveries observationally, and so we're still kind of continuing to push limits on the thickness satellites that we can discover. But I would say that really the kind of major change in the picture was when we stopped comparing the luminous satellites around the Milky Way to dark matter clumps in the simulation, but to actually set luminous satellites in the galaxy as well. And so if you look into the recent simulation from the FIRE team of their Milky Way size galaxy, we see that they form satellites and kind of in numbers that are very consistent with what we see in the Milky Way. So it would look like that there is really no more missing satellites problem in terms of luminous satellites. But what and the solution then is just that some of those dark matter clumps don't have stars. But if we look at the dark matter picture again, it really says that there should be structure, and even though we can't see it because it doesn't produce stars, there is still a prediction of this model that there should be empty dark matter clumps, so they're roaming around the Milky Way. And so this was stated in this review I mentioned before, And it really looks like this is the thing to test the CDM paradigm, to finding this low mass lumps of dark matter that don't have stars associated with them. And kind of the transition mass that we are looking at, we're hoping to measure it, something like 10 to the 8 solar masses. And so, okay, it's a hard problem, right? Because if these are inherently dark, they're really, we think that dark matter is only weakly interacting, that we kind of only hope is to find gravitational influence of these small clumps onto things that we can't see. And people thought hard about it, what to do, and it turned out that one promising avenue is actually through gravitational lensing. So a couple of years ago, Astrophysics had a paper showing that there is kind of a class of lenses, and shown here, so the lensing galaxy is in grayscale, is seen to be optical, and it's the object that is being lensed is a star-forming dusty galaxy, so it can be observed with Alamine. So these are the red contours over here from the Alamine radio telescope in the submillimeter. And what they did was actually try to, since they see the lens model, try to model the distribution of the light of the lens galaxy. And it turned out that just a smooth model of the galaxy of the lens that is seen is not enough. And so here is their figure showing that if you include a subhalo, like a clump of matter, in addition to the smooth galaxy in different parts of the space, you can get a better fitting model. So the red pixels are showing where the model fits better if there is a subhalo, and you can see that they get a much better likelihood if there is a subhalo over here. And so it looks like, and like in this image, you don't see it. So it looks like they have discovered a dark satellite of this galaxy, SDP-81. And the hope is then that we can discover, like in this way, look at into more systems, so there's more such systems where we could kind of build up this, or kind of just count how many there should be and get the mass function from this lensing modeling. However, it looks like, at least that the first detection that was made was got a mass of something like 10 to the 8 solar masses. And in the Milky Way, we still kind of see stars and satellites of that mass. And so we kind of really push the limit and be able to study these clumps if they exist in detail. We would really like to see, to search for them more locally in the Milky Way. And so this is what we'll do in this talk. And the first thing we need is something to really trace the gravitational potential for us, so we can't really take the same approach of lensing. So we need to find objects in the Milky Way halo that would be sensitive to these gravitational perturbations. And the second part is then to see if when we have a sample of these objects, do they actually show any deviations from a smooth distribution of matter. And so to switch our gears a little bit, here is the Milky Way as seen from 10 star survey. So it was, this is still ongoing survey on Hawaii that imaged 3/4 of the sky and in multiple bands. And here is the color image. And so, most of the stars are in this, and here's the bulge, and the halo is over here. And you can immediately see that there is going to be a problem studying the halo because there's barely anything there. If you squint a little harder, you can see that there are some dots visible, and so those are the mainly blood-borne clusters and some dwarf galaxies in the halo. So there is stuff there. It's just harder to find. At least if we only count stars, like what is done in this image. However, we can be harder and then try to target stars that we think would be predominantly in the halo to see whether we can go find those tracers that we wanted to trace the dark matter with. And so if we kind of zoom in on one of those clumps on the globular cluster and look at the color magnitude diagram here, showing the G- star versus G color, you can see that the stars have a specific track in the space, and so it's really consistent with all of the stars being drawn from a single population. So here is the stars that are low mass and still burning on the main sequence, burning hydrogen, and then over here on the giant branch, and even here there's fairly consistent blue horizontal branch over there. And so this is important because if we only look in the field of the Milky Way, just some generic part of the galaxy, the color magnitude diagram looks much smoother. It's in a way a superposition of tracks like the one that of a single age and single metallicity population, and so there's just a range of ages, a range of metallicities, and also a range of distances that these stars are from. So what you get is like this much smoother distribution that also has a huge peak over here, and those are all of the more metal-rich stars that are better. And so in detail, if we compare these two distributions, we can see that there are some regions of this color magnitude space where there are preferentially more stars in the globular cluster diagram than in the field Milky Way. And so a very simple exercise is to just bin this space and divide the two diagrams. And so in a way, here you're kind of seeing where the contrast is the largest between the globular cluster population and the field of the Milky Way. And so you can see that if you're selecting stars in this box over here, you're most likely to be selecting stars that are similar to the globular cluster population. And so what people then did is to filter a map like this, and that is just kind of a number counts of stars per pixel, and weighted them by a filter that looks like this. So kind of upweighting stars that are faint and blue and more likely to be members of old metal core populations. And what we ended up with is that something, a map of the halo that looks like this. So as before, you can see that there is still a lot more of these small dots, the bound objects, the dwarf galaxies, and the globular clusters. But there's also a lot of this large-scale structure. And here, the color just maps to different distances in this map with the SSS data. And the most prominent feature is the Sagittarius stream, shown over here, which is very wide. But then there's also smaller accretion events, such as this orphan stream over here, that we also think is from the dwarf galaxy. But then we see a disrupting globular cluster here in the corner. This is the Palomar 5 cluster, and it has two tidal arms extending from the cluster. And we even see completely disrupted objects such as this one over here, which is the GD1 stream. And so it's been really exciting when it first discovered, because it really immediately very visually shows you that, or confirms this picture of hierarchical growth of galaxies by mergers. So it really, in a way, also confirms this picture put forward by the lambda CDM simulations of galaxies grow through mergers. But it does even more than that, and that's because it turns out that the shape of these streams actually depends on the distribution of matter in the galaxy that formed them. And so to just quickly visualize this, I'm here showing a model of a stellar stream, and it's in just some coordinates on the sky, kind of aligned with the stream itself. And so we understand this disruption of satellites fairly well, and can create in a model of a galaxy that looks something like the Milky Way, that has a disk, a bulge, and a halo. We can create a model of a stream. And then the colors are just coding the radial velocity here. And so if we then start changing the properties of the galaxy, like increasing the mass of the halo or increasing the mass of the disk, the shape of this stream changes, and also the velocity structure that we can measure along the stream. So we can kind of think that we can almost, from the shape of the stream, and it's and I guess not just shape on the sky, but also distances and velocities, we can kind of backtrack what the potential or the distribution of matter in the galaxy is. So if you watch closely, you can see that like some changes in the galaxy produce the same effect in the stream, so there are degeneracies. And to kind of quantify a little bit more, what we can do, we actually perform a full picture analysis to quantify the actual information of how well you can constrain parameters of some smooth potential given the current data that we have on streams. And so here is a picture of the sky distribution of some streams that we use in this analysis. And we have streams that look kind of like the streams in the Milky Way that are known. They're in this small galaxy, and then there we can exactly calculate from the distribution of or the measurements of the streams how well can we measure the halo scale velocity. And it looks like we can measure it pretty well. So the saturation here at the color bar is 25%, and this means that with most of the streams, with the data that could be currently available, we can measure the total mass of the halo to better than 25%. And interestingly, like different streams have different sensitivity to this parameter, so it kind of also tells us where to focus our resources. So it turns out that this GD1-like stream is very informative and can get very precise measurements for the scale velocity, and also, as it turns out, for the shape of the halo. So this is now the same deal where the color of the stream is telling you how precisely we can measure this parameter. Just instead of the scale velocity, now we're showing the flattening of the dark matter halo along the x-axis. And interestingly, now some like streams like the one that I showed GD1, is supposed to provide good constraints on both parameters, but some seem to be like this Spencer's 1A is much more informative about the shape than the total mass. And so it looks like that each stream can contribute something individual to this kind of global picture of what the distribution of matter in the galaxy is. And so what we would ideally want to do is actually try to combine all of those streams simultaneously. And to just quantify what effects you could gain by doing this, I'm showing here how the precision in the derived parameter depends on the number of streams that you use to derive this estimate. And so all of the gray points here is just like for a single combination. So if for any stream individually, it's like here on one. So and then if we select two streams from this sample, those are the pairs over here, and then the median is shown with a big white circle. And so you can see that the more streams you included, the better the constraints. And if you include more than 10 streams, it looks like the precision is better than 1%. So this looks like there is a lot of information in streams that we could harness by combining all of the streams simultaneously together. But at this point, you can say like, wow, that's great. it's really precise. All of the, because just to put in perspective, the mass of the Milky Way is like, it's been uncertain up to a factor of few. But then there's to remember that here we really are testing only a simple model that assumes that the dark matter halo is smooth and triaxial. And I think at this level of precision, if we can really achieve it, this assumption will no longer hold. And instead of just having a few parameters in our model, we'll have to probably have more. And to kind of understand what we are actually, or what is the underlying physical quantity that we are actually constraining, we did an experiment where we propagated this uncertainties on individual parameters of the halo and the disk into something physical, and we chose the radial acceleration to do that. And so the radial acceleration is mainly, you can think about it as something like the enclosed mass. And I'm showing here for the two streams how this precision or relative precision in radial acceleration depends as a function of changes as a function of distance or position in the galaxy. And so you see, like the two streams provide very different numbers. So one is much more precise than the other one, but they both have this same shape of the curve, such that it has a local minimum at some point in the galaxy. So it looks like it's not that every stream just measures the acceleration or the enclosed mass everywhere equally well. There is a specific location in the galaxy where this measurement is done better. And the fact that that these two curves are offset, so that there is like a different normalization for the two streams, it really comes from the stream length. So it looks like that streams that are long just have a more precise measurement of the radial acceleration, so the minimum of that curve is lower. And as for the location, it relates somewhat to the current position of the stream at the present. So here on the y-axis, I'm showing the minimum location of this minimum over here for individual streams as a function of the current position of the stream at the present. And so in general, it looks like that streams that are farther away also have this measurement of the radial acceleration that's also farther away. But this is off from this one-to-one line that we might naively expect if we think that the streams are kind of giving us a local measurement. But on the other hand, we said that we do only have a simple model of the galaxy, and so it could be that really what the streams are measuring is the enclosed mass at their current position. It's just we can't see it with the model that we are using here is not flexible enough to reveal that. And so just to test this hypothesis a little further, we introduced more terms or added flexibility to our model of the galaxy by adding this dipole and quadrupole terms as kind of perturbations that we could constrain. And since this introduced additional parameters to our model, it turns out that all of the model was more poorly constrained. So you can see that at all radii here, this other perturbed model produces worse constraints for both of the streams. By the way, what it also shows is that it is kind of getting more narrow or better confined spatially. So both of these local minima are becoming sharper. And when you look at where the curve is kind of zeroing on, it looks like that all of those, they were like very far off from the one line, they're kind of starting to get closer in. And when we include even more terms, so up to the octupole terms, turns out that all of the streams have their best measured radial acceleration within 1 sigma from their current position. And so what we are taking from this is that streams actually do look like they are measuring local properties. And planets or the mass enclosed within their current location. And it's really interesting if we think then of individual stream as like a probe that we have somewhere in a different location in the galaxy at a different distance. And with the new data from the survey, and here also showing from Gaia on whole sky, we do have streams that are at different locations in the galaxy and also different distances. So there is all so yeah, the color coding here is by distance. So the yellow stars are just much more distant, and the purple ones are kind of around 10 kiloparsecs from us. And so what we're then hoping these days is that we have this network of tracers that we can really start measuring more non-parametrically what the distribution of matter is in the galaxy, and then combining information from all of these streams into one single consistent picture.
Anna, can I ask you?
Yeah.
What is it that you're assuming that you know from each of these streams beyond some number of stars at some distance? Presumably your model has radial velocities, maybe proper motion.
Yes. So the plots that I showed so far have all assumed that we have both the distances of radial velocities and the proper motions. Not all of them are measured very well, like the distances we assume that are kind of like 20% uncertain, just from the main sequence turn off of the stars. And something like proper motions and radial velocities on the order of 5 kilometers a second uncertainties. So it is. So while we don't have the data for all of the streams at the moment, it is data that is obtainable. So yeah. So it really is something like that we could do soon to map at least the inner part of the halo where most of the streams are, and map like the distribution of the smooth matter. And it really comes from this expectations that in a smooth galaxy, the streams look like this, like narrow, one-dimensional strings, where and that from there, the shape of this distribution, we can learn about the underlying distribution of matter. However, another aspect of the streams is that if they live in a clumpy galaxy full of, say, subhalos, we might not see a stream that looks like that, but instead see something that is much more disturbed. So here I'm comparing two streams, one that was produced in a smooth analytic halo, and one that was produced in a cosmological halo from the Via Láctea simulation that has subhalos in it that are interacting with the stream. And so you can see that in this case there are much larger density variations along the stream. There are these gaps, there are the stars that are picked out from the stream itself. And so then the hope has been for some time that finding gaps or finding this density variations along the stream will tell us something about the number of encounters that streams have had with these perturbers, and then presumably tell us about how many there are in the galaxy, and then that would map that to what the dark matter is. However, this has been really hard so far because the data look like this. So here is, and I will zoom in on the GD1 stream that I showed, the very long one on the map of streams overall. And I was just in this coordinate systems, but these are just sky projections of that are kind of aligned with the stream itself. And so, yeah, while you can definitely see where the stream is, there's like this dark track. Over here, it's kind of hard to really pinpoint a believable gap. You might say, oh, there's it looks like there's fewer stars over here, but then you can see like this, even in the background, there's density variations of this magnitude. So it's been kind of really hard to to say something very quantitative from purely photometric data alone, or I should say maybe photometric data of this depth at the SDSS level. However, this has really changed 5 months ago, because Gaia mission had its second data release, and so in addition to knowing colors of stars, like shown over here, so this is just average color in like very small pixels as seen by Gaia, we now also know how stars move. And I'll show here is just very like inner view of stars that are close by and moving very fast, but you can kind of see that now if you're interested in this group of stars, you can now identify it much better and separate from the whole foreground, because you know that they should not only look like that, have similar colors, but also be moving together. And even though this movie is for the nearby stars only, for something like 7 million stars, where we have both the proper motions and the radial velocities from Gaia, we have proper motions for 2 billion stars. So almost all of the Gaia's catalog has proper motions now. And furthermore, these also stars that are nearby have measured parallaxes, so we know that they are nearby. If we're interested in the halo, those measurements are not that good at the moment, but at least we can kind of remove the stars that we know are nearby from our sample. And so since that GD1 stream looked to be very constraining because it's so long from our previous calculations, then we decided on this, when this data came out, to just see what the stream would look like in the Gaia data. And so we started this kind of new selection of likely members of the GD1 by at first selecting just the distant stars. And this is again those coordinates, the phi1 and phi2 that are aligned with the stream. So we should expect the stream to be at phi2 of 0. And if you just select the distant stars, you still don't see anything, because there's still a lot of Milky Way stars in the halo, and some also in the big disk. However, if you look into the proper motions of this space, it looks very clumpy, and it has 2 clumps that are very big, and one is the disk, the other is the halo, in this coordinates, and then there is like a small outlier left over here. It turns out that these stars are mainly GD1 stars. So if you select that, you can immediately see that the stream pop out. And just to kind of draw the attention here, we no longer then, we can actually just individually see very likely members of GD1. We no longer have to have that kind of probabilistic approach that kind of only, the stream only appears if you look at it in pixels. But then we can go further, since we still have our color information. That was the only thing that we used before. And so if you look into the color magnitude diagram of this space, we can again see that old MEL4 track over here. So if we just kind of select the bottom part of it, the main sequence, we get a very clean map that removes a lot of the contamination from this field, and are mainly left with GD1 stars. And so what we immediately saw was that at first that the stream is much longer than we initially thought. So now being able to remove so much of that contamination, we found this very low surface brightness extension of the stream that is turns out to be more than 20 degrees longer than we initially suspected. And also now that we have such clean or such good control over contamination, we can actually say that those gaps that we see are actually confidently that they are density variations in the stream and not some feature of fluctuations in the background density of stars.
Pardon my ignorance, is there a reason why there are no stars of the positive phi ones in this case? Is that like the end of the
Yeah.
stream? Is that where the main?
Yeah, we tried extending it over in this region, and we couldn't really find it. Like even this part is kind of, I think, more tentative. Just kind of, if you hover over here and we'll just look at this part, you'll be like, I'm not sure, but if you kind of see it, you can kind of convince yourself maybe that it's extending. And it is, so our selection is getting less efficient in that region because there is a proper motion gradient along the stream. And so the stars of positive phi 1 also have proper motions that are like this and are getting closer to this other blobs, to the contamination. And in general, there's, yes, I mean, it's so long, so you're actually getting into the low galactic latitudes on both sides of the stream. So there's even more stars, and then our solution is less efficient. So, yeah, it's unclear, like, how much longer the stream is extending here, but we couldn't really see it in the data alone. So let's say, yeah, with some large spectroscopic survey, I think if it extends, it should be possible to see it because we now have very good predictions of what the stream should be doing from just the rest of the 100 degrees that we have to do. But yeah. Yeah, and that's and it's a good point to kind of stress that it might be extending further because we think that there's no identified progenitor even like in this more high resolution view of the stream. And at first we thought that it might be that the progenitor is somewhere over here, disrupted over here, or it's like in the final stage of disruption because this is kind of the densest part and the thinnest part of the stream. But we also found an equally well functioning model that kind of puts the progenitor over in this one gap, so we can kind of explain away one gap with a progenitor that's completely disrupted here fairly recently, so that the gap is not filled in. And so these are kind of the two sides of the stream. And if that's the case, or like you would expect it to be somewhat symmetrical, and there is a distant gradient of the stream, but yeah, it's definitely interesting to see if it extends on this side as well. What I'll be mostly focusing on for the rest of the talk is these two features, and so it's a kind of a test on your astronomer eyes, whether you can see features outside of the mainstream. And we identified these two kind of blobs. One is an overdensity over here that looks more fuzzy, and then there's a small narrow overdensity above the stream right here. And this was really unexpected because we, or rather, people really studied gaps and like in interactions with of a stream with a subhalo. It's clear that gaps are easily produced and could be detected, but yeah, there's just not an expectation that we would ever be able to detect something like the stars that are outside of the stream. And so just to kind of firm this up a little bit, as it is kind of a fairly I guess visual inspection in this figure, we can try to model this distribution of stars with a combination of Gaussians for in the phi 2 direction, so that we have a set of two components for the model stream, then a smooth background model, and then allow for there to be a Gaussian component on either side of the stream. And so if we do that,
Actually, guys, that's a quick, this
Yeah.
story, the blob,
Yeah.
did they satisfy your color confirmation? That's good.
Yeah.
They're all like,
yeah, so they're all, yeah, and we did look into detail into both of those, and they're not like random like over densities. There's like clear, so that since there's the proper motion gradient, so the proper motions of the blob are similar to the proper motions of this part of the stream, and for the spur it's similar.
So you like first identified them in proper motion and color space, or did you first identify them?
Yeah, we first identified them here, and I was like, okay, and then we looked into detail, and it looks like that they are consistent with kind of, stream stars that are kind of adjacent to the part. And so if we then define a sort of a membership probability for each star based on those likelihoods that is drawn from the galaxy, and we see that we get 0 probabilities for stars in this region of the spur, and like some lower probability in this blob region that these are actually stars. That this is a separate component in addition to the smooth background, so it's not consistent with just being like some variation in background. And since with the Gaia data and some radial velocity that were obtained earlier, we have the orbit of the G1. We can then create a model of the stream in smooth galaxy, and I created a model that constructs the progenitor or in this gap. And this is what the model looks like. So it has this almost completely empty gap as its coordinates by 1 of -20, but then doesn't really have other features. So it looks like that to explain those variations and stars outside the stream, we would need something in addition to this simple model. And as I said before, we will have studied what encounter of a subhalo with the stream would look like, and so this is from one of the first papers that were spearheaded this effort, showing just a gallery of different end results from a construction of a stream with a subhalo. And you can see that mostly forms gaps, but there are like in some cases it kind of does look like there's a spur or something like that. But then after this, there's really hasn't been much talk about this folding of the stream or stars ejected from the stream. It was really mostly on what can we learn from the gaps. And so here's just you can see how if you change the velocity of the encounter, that gaps of different sizes, and also how close the encounter is to the stream, and also how massive the perturber is. You can get gaps of different sizes. And so there's been just a lot of work studying if you measure the profile of the gap very well, you can start to constrain some of those properties. But there really hasn't been much work on stars that are kind of outside of the stream in this context. And so in order to explain GD1, we wanted to, we really would need to vote. And so we started with like a very simple experiment to just see if the encounter is still a viable option. And so we started with kind of a string of stars that are like this case, not even moving, so they're just in free space. There's no gravity. There's just this one perturber that here goes along the z-axis and passes like right here at 100 parsecs away, and then just continues on. And so when it passes, the stars that are closest in, they get a velocity kick and start moving towards where the perturber passed. And as time goes on, they reach this point and then start moving in the other direction, forming this loop of stars. And so you can see that in this very simple experiment, you can get stars kind of outside of the mainstream, and if you project this feature, this loop, in different ways, you can sometimes get morphology that we can say like, oh yeah, this will be identified as the spur. But in this case, we no longer have a gap, so we still want to explain both the spur and the gap. And so we went then like one step further, and instead of having this simple model of a stream in a free space, we put it in a galaxy.
When you say massive, how massive?
So this is like a few million solar masses. So
source, or?
Yeah, this is experiment with a point source, yeah. We're just like doing like the simplest thing in all, and then just show you further. And so our then next kind of more complex thing was to put this stream in a galactic potential. So here I'll show a movie of stars on circular orbit in a logarithmic halo, which shows that because it has a flat rotation curve, so it looks kind of like a galaxy, but it's still very simple. And we again have the same experiment. We would pass the perturber, point mass perturber, just below the stream, and then see what happens. So the loop still forms, but it kind of rotates around the stream, and with some projections, it forms this, just later on, okay? Since there are like stars on either side of the loop are moving faster or slower with respect to the stars in the neighboring stars in the streams, that's how the gap opens, and then in some phases or some viewing angles, it looks like some part of this loop is right behind the stream, and then only one star of the loop is sticking out like the spurt that we saw. And so I thought, okay, maybe if we project this not in the space coordinates, but in angular coordinates, we might get something that looks like the GD1. So here is GD1, the gap and the spur, and here is what we have for this simple model in a spherical halo on a circular orbit. That really does look like that loop of stars that we saw. And in a simple example, it's kind of extended. This one side is a spur, and then it has the other side aligned with the stream itself. And so this looked very promising, and so I wanted to revisit our simple model of the stream that now has actual width, and it's like the actual GD1 orbit in a galactic potential, or what we think is the galactic, or fairly good approximation of the galactic potential. And then when we include a perturber with this model, we get something that looks like this. And so we still have that gap of the projector, but now also there is this other gap caused by the perturber, and then some stars are flung out almost 10 degrees in this projection. And so visually is looks like this is a viable option, at least. It does explain many of the features that we see in the data. And we have some parameters of this perturbation. So it seems like this model happened almost half a gigayear ago. It's a few million solar masses, and it passes really close by to the stream. But it is also very compact, so it is no longer a point source, but still it's a Hercules profile with the scale radius of 10 parsecs, so very compact, or something like 10 times more compact than what we would expect from a dark matter, naively expect from a dark matter subhalo. And so okay, we were pretty happy with it. At least we have had a explanation for what happened to GD1, and then we just want to see how much room there is with this in this parameter space, whether we can even just with this morphological kind of examination, if we can constrain some of those parameters. So by comparing the gap position and size and the location of this spur over here, we evaluated a number of models, and these are the constraints we get on the time of the encounter, the effect parameter b, the velocity, and the scale size and the mass of the perturber. And so it looks like it had to have been a fairly recent event. We don't really have very old cases that produce those features. It also looks like it passed fairly close to the stream. There's this mass velocity degeneracy, so meaning that if the perturber is moving faster, but it's more massive. It's a similar effect to a lower mass perturber moving more slowly. And another finding is, yeah, that it really looks like it should have been very compact.
So what's
object.
so where's the velocity is what? Is it 372 or is it looks like it's 40? What's the best of velocity for this?
Yeah, so it's actually, yeah, it's kind of at this, it's cut off way prior. We have it at,
That's a very large velocity for the collecting for
Yeah.
for us like it. So it's like basically escape velocity.
yeah, so we did a kind of blind search. We could impose a prior on velocity to
So but I'm reading it correctly right now. Basically, according to this figure, the best fit mass is 10 to the 7 or so, and
Yeah.
best fit velocity is 480. That's a true statement reading this figure.
Also, we don't have a full generative model of for the stream, so it could be that this is just yeah, that this is like, this is not really the best velocity, just some kind of artifact of the likelihood as we defined it. I think, yeah, more, I would believe the degeneracy in this direction. I would say, yeah, they're probably all, like, if you look them by eye, I would say they kind of look really well, all the models in that kind of direction. But yeah, it does look like it is preferring very high velocity passages. Yeah, and just for reference, the model I showed before is here, so it is kind of at this more diffuse end of the mass radius plot. And so then the next question is like, can we tell what this perturber is? So we have the orbit of GD1, as I'm just showing here, the past 5 gigayears or so in the galactocentric coordinates, so Z on the y-axis and the I guess cylindrical R on the x-axis. And so since we have that, people have now with Gaia measured the orbits of the known objects in the halo, the satellite galaxies and who knows, and global clusters. So we can actually check how far they were as we go back in time. So here is the relative distance between the classical bores and the darkest and the ultrafaints and the global clusters and the GD1 stream. And you can see that they don't really come close enough to have caused this perturbation. So all of the we would require our input parameters to be something like 10 parsecs, and nothing really comes within 1 kiloparsecs from GD1, except for the disk of the Milky Way. So here the disk crossings that are in there happen on the similar time scales to what we derived at the time for the encounter. And so it was, yeah, wanted to check, could it have been something moving at this, because he'll suggest that also giant molecular clouds could cause such features, but since we have the orbit of GD1 and know how it crosses the disk, we know exactly what was the relative orientation between the stream and the potential GMC that would be moving on circular velocity in the disk. So we can create a model of that interaction and figure what the first disk crossing would look like, and the colors are just showing where the molecular cloud was with respect to the stream. And so you can see that there is a gap open at the right location, but the stars are like in this loop are in the wrong place. They're kind of below the stream here above. And second most recent disk crossing, again, you can form a gap that is approximately the right size, but then all of the other stars in the loop are again in the wrong positions. And so it looks like it would be hard to to have created this with a molecular class or things like we can rule that out. And so it really does look like it is some dark object that is massive, and the hope would be to go find it with some other means. Unfortunately, we can provide very good predictions of where the perturber should be at the present, because just based on the spatial distribution of the debris, which I'm showing on the left, just for a few samples from our posterior distribution, you can see that they all kind of produce a gap and the spur. They're kind of looking right, but then in the velocity, radial velocities, they have a very, very different structure. So there are very different orbits, and so that we can't really predict where the thing is now. But we are working on it and have observing time coming up at the end of November to try to measure radial velocities, and so we can perhaps then tighten the area of like where we could search for this perturber. And there have been several suggestions of how to look for for dark matter subhalos. And the first one is like just if it's dark matter, it might be annihilating. If you know where to look, you can actually go into Fermi data and see if there's like an axis with respect to other regions. If it's a massive object, it should also affect stars in the galaxy, like if it crosses the disk and if it's massive enough, it might perturb some part of that. Or just in the halo, just even in the halo, it should affect the motions of stars. So it should be kind of locally attracting stars. And if we have a more targeted search, we might be able to see some evidence of that. So with that, I will close. It really looks like that solar streams will be really informative for the distribution of matter in the Milky Way halo, both on this global scales when we start combining multiple streams simultaneously, and also on local scales where you can get, because we do see this feature in one stream that looks perturbed, and we have a model that explains this qualitatively that the gap in the stream and the stars outside of the stream in an encounter scenario that might be relevant for the dark matter paradigm. So thanks.
Are there any additional questions?
Just out of curiosity, when you said you have time in November, where is this stream? Is it visible from Chile, or are you using Magellan? Or?
No, it's with MMP, so
Ah.
it's a northern sky. Yeah, it's more of a spring target, so it's just starting kind of coming out second half of the night.
No, right, because it's slow, so it has to be.
Yeah. Original Philo streams.
Yes. So you said there was this mass velocity distribution. So what's like the smallest mass? Like let's say you go back to your simple example of a point mass hitting a stream. Like what's the smallest mass thing that could come in that actually creates a visible effect on the stream? Like 100 solar masses, 1,000 solar masses.
I think it's 1,000, so I can pull up this. So yeah, right. So I guess kind of like two sides to this question. So I think in principle, like any small perturbation should have an effect, at least in kind of scattering stars. Also, it would kind of pop up the stream. And I think even like 1,000 solar mass perturber would eventually create a gap. It would just take a longer time. But I think to create the spur that is kind of, there's only a limited time that the spur stays visible. So I think to have both, couldn't have been too low of a mass. So here showing from from our visual model, if you change the mass, so this is like n-6, and this is, yeah, like 4 times n-6, and this is 1 times n-6, and you already only barely have the square, so. Yeah.
So, my asymptotic question would be, do you like rule out like a pencil or a star or something like this? I don't know, it's like, that's just like,
Yeah.
what happened. At this scale.
Yeah, I guess, that's a calculation that could be done, right? Because I guess you could, right, combat the low mass with a velocity, but I think it would be like for 10 solar mass, it would be like something like this. Yeah.
Are our distance uncertainties on the star ever going to be low enough that we can discriminate like a loop
Yeah, that's a really interesting question. I guess. I mean, I don't think parallaxes would be good enough, but we were getting spectra, so the spectra for the metric distance. So, like from a spectrum, you would get like the luminosity of the star, and you would then get a better handle of the distance. I kind of think it would be still very hard to do, but it is a really good point. Yeah, because in most of the models, we do have this side of the loop over here, and yeah, I think it might be hard in distance, but what we are hoping to do is to get very precise proper motions. And so if that's, yeah, I guess depending on exactly like the velocity direction at which something will pass, you would expect there to be a velocity offset in the proper motions and radial velocities within these two parts of the stream and the loop. So I think that would be perhaps a more easier way to confirm this.
Go ahead, thank